Welcome to Weather Extra on CBS News Bay Area. I'm KPIX 5 meteorologist Paul Heggen. Every week, we're taking a closer look at a weather topic, a deeper dive than what we can do within our daily weathercast on KPIX. This week, I want to explore the atmospheric effects of the volcanic eruption near Tonga a few weeks ago. That eruption sent a tsunami across the Pacific Ocean, one that actually caused an estimated $6.5 million worth of damage around the Santa Cruz harbor. But let's start with the eruption itself. It originated underwater, under an island called Tonga Ha'apai. The explosion has been estimated to be equivalent to 10 million tons of TNT. That's 10 megatons, equivalent to the largest nuclear weapons the United States tested in the Cold War. The eruption actually split the island in two. Its power was in part related to its location, about 500 feet underwater. When superhot molten rock or magma hit seawater, the water instantly flashed into steam, expanding the explosion many times over. These were almost perfect conditions for this kind of event. Had it been much deeper, water pressure would have dampened the explosion. Had it been shallower, there wouldn't have been as much seawater to amplify the explosion. The shockwave produced by the eruption rippled through the Earth's atmosphere at 680 miles per hour, nearly the speed of sound, circling the planet twice within a day. Barometers detected pressure changes of 2 to 3 millibars as far away as Europe as a result of the passing shockwave. These satellite images actually make the shockwave visible as it expands, and meteorologists watching over Europe and Africa were able to distinguish the rebound of the atmosphere caused by the explosion on the other side of the globe. In the United States, airport altimeter data recorded the effects of the shockwave. If you just look at the dots, you'll be able to see it rippling across the country from west to east as the pressure changes. The eruption also injected a huge amount of ash to record altitudes in the atmosphere. Satellites detected the ash cloud reaching over 24 miles above the Earth's surface initially, according to those initial observations by Oxford University researchers. Subsequent observations have estimated that part of the plume climbed 34 miles. That's through not only the troposphere, the layer of the atmosphere where weather occurs, but also through the stratosphere and into the mesosphere. This is the first time that volcanic ash has been detected so high in Earth's atmosphere. So let's turn to the potential climate impact. Volcanoes like Tonga that send huge amounts of sulfur dioxide into upper layers of the Earth's atmosphere can sometimes produce a measurable cooling effect on the planet's climate. This effect was detected, for example, after the 1991 eruption of Mount Pinatubo in the Philippines. That eruption was the second most powerful volcanic eruption of the entire 20th century, cooled down the planet in a way that was measurable for 2 to 4 years. Pinatubo erupted for several days, sending about 20 million tons of sulfur dioxide gas into the stratosphere, that second layer of the atmosphere. There, the gas combined with water to create aerosol particles that reflected and scattered some of the sun's rays, keeping them from reaching the Earth's surface. That had the effect of cooling the atmosphere by about 1 degree Fahrenheit, or half a degree Celsius, over the course of several years. But here's the difference this time around. Despite the apocalyptic proportions of the Tonga blast, the amount of ash it contained was relatively small compared to other large volcanic eruptions in previous centuries. According to available data, Tonga blasted into the atmosphere about 400,000 metric tons of sulfur dioxide, about 2% of the amount of Mount Pinatubo. All of that means that the volcano is certainly not going to buy humans any time in our battle against climate change. Despite the lack of long-term climate effects, scientists are going to be studying this event for years because of the shock wave produced by the explosion, as well as the unusual nature of the tsunamis that it generated. Tsunamis were detected not just in the Pacific, but in the Atlantic, Caribbean, and the Mediterranean as well, which means either the atmospheric shock wave was strong enough to prompt tsunamis in those other bodies of water, or some kind of shockwave actually propagated through the Earth itself, which is just some mind-blowing stuff to think about. That's it for this week's Weather Extra. Meteorologist Aaron Peck will be back next week to cover another topic, and we are inviting you to play a role. If you have a weather or climate question, just email it to weatherextra@kpix.cbs.com.